Let's do some examples. So let's start simple. So you're going to look at some series circuits. So resistors, they transform electrical energy into thermal energy. Let's draw a simple circuit. So I'm going to draw 3 resistors in series. So not a great drawing, but get the idea. So let's say this is 6 volts, and this is a 100 ohm resistor. This is a 500 ohm resistor, and this is a 300 ohm resistor. So first thing, when you get any circuit, you want to basically create the simplified version of that circuit, the equivalent circuit. So basically, what circuit? So if we had just a single resistor, what resistor would we need to get that same current draw is basically what we're asking. So 6 volts, what would we need to get the same effect? So this is 100, 500, and 300. So resistors in series, very straightforward, just add them up. 100 plus 500 plus 300, that's 900 ohms. So what we're saying is that if we had a 900 ohm resistor there, instead, it's going to draw the same current. So again, so our total is just 100 plus 500 plus 300 to get a total of 900 ohms. Now we can actually find out what the current draw is. That's just voltage divided by resistance. So we get 6 volts divided by 900 ohms. And we find out that's 0.0067 amps. Or we can also say 6.7 milliamps. So both these two circuits, they are drawing 6.7 milliamps. So because it's a single path, if you put an ammeter anywhere, so I can put my ammeter anywhere. I can put the ammeter there, I can put my ammeter here, I can put my ammeter here. They are all going to measure the exact same value. So all the electrons, they move together. So think of if some electrons are moving with some speed at one point, it must also be traveling at an electron somewhere else in the circuit must be traveling at that same speed. So wherever I put the ammeter, it's going to give me that same 6.7 milliamps. We can go to the next step, say how much voltage is being consumed by each resistor. So because I gained 6 volts from the battery, all 3 resistors must combine to consume 6 volts. So this first one's straightforward. It's 9. This is one resistor. So if I gain 6 volts here, I must lose 6 volts at the 900 ohms. But it's more interesting to say how many volts are actually being lost at the 100, the 500, and 300. So we can actually just go back and calculate those if we wanted to. V equals IR. We now know the current passing through each of those resistors is 6.7 milliamps. By multiplying the resistors by 6.7 milliamps, so 0.0067 times 100, you see that this first one is going to consume 0.67 volts. And if I did 500 multiplied by that 0.0067, you say, this one's going to consume 3.35 volts. And 300 times 0.0067, that's 2.01 volts. If I add up all those, of course, just some rounding. Due to rounding, it might be off by a little bit. But lo and behold, so these ones all adds up to 6.03 volts. So I add up all those things, that equals to 6.03 volts. And that's within a close enough margin of error. So that's just due to rounding. Okay. And that's because it wasn't actually 0.0067, it was actually 0.00666666, so on. So that rounding up caused our final result to also be a bit higher than expected. Here we can do another question. Scroll down. So I realized this is where I was planning to put the work for the actual voltage across each one. So if I were to redraw this again, again, 6 volts right here. We got our 100 ohms, 500 ohms, 300 ohms. If I actually said this is resistor 1, resistor 2, and resistor 3 at 1, we can solve for V1 equals IR1. That equals to 0.0067 amps multiplied by 100 ohms equal to 0.67 volts. Then we had V2, we got 3.35. So yes, so I just meant to put the left space here so you didn't have to cram it in, but kind of forgot. Again, voltage gained, let's equal to voltage consumed by the resistors.